Okay, hello everyone. Thank you for joining us in this session of John Conway Seminar Series. Today our speaker is Professor Mercedes Rosas from University of Seville in Spain. She is a professor in the Department of Algebra of the University of Seville, and her area of research is algebraic combinatorics, and she has extensively published in this area, and she is supposed to discuss about non-intersecting passes and the determinant of the distance matrix of a tree. Professor Mercedes, thank you for accepting our invitation, and over to you.
Thank you very much for the invitation. I think there are some people waiting to get in. I see.
Yeah, I accept them.
Okay, perfect. Okay, so I'm Mercedes Rosas. I'm going to work with a joint project. It was a fun project because it was between me, a frequent collaborator, Emmanuel Brian, and three students that were essentially undergraduate at the point. Luis Esquivias, that is now doing a PhD at Sevilla. Álvaro Gutiérrez, that at that point was a master's student and is doing his PhD at Bristol, and Adrián Nilo, that is also working now towards his master at Sevilla. And since this is an online talk, I decided to spend a couple of minutes just. Okay. So first I wanted to say, where is Sevilla? So we are in the south of Europe, in the south of Spain. And I just check on Google Maps, it's like 13 hours by plane. Well, I guess it depends a bit on the connection, but we are far. And Sevilla, well, Sevilla is a very beautiful city, as you can see, it's full of history. Many civilizations have lived here, the Phoenician, the Roman, the Arabs, the Visigoth, and nowadays the regular civilians, and you are all welcome to visit. And until that's a couple of years ago, there was a big celebration in Sevilla, because here is where the trip of Magellan started. It started in Sevilla, it went all around the globe for the first time, and ended in Sevilla. Well, he was dead, but that's a detail. So a couple of years ago, it was 500 years from that trip, and I saw that it was a nice alternate title for my talk on routes and maps and distances, because this is what I'm going to be talking about. So
great.
So let's start now with the story I really want to talk. And it's not so old as the trip of Magellan, but it's old enough. From the 71 of last year, and it was started by Graham and Pollak. And they were looking at the distance matrix of a tree. So I want to take our time to be sure that the object of the talk is true. So we have a tree. I'm always going to be working with the same tree in my running examples. And when we define the distance between the two of the vertices, just as the number of edges you have to travel to go from one to another. So since the tree is connected, you would always get a number, a natural number. So let's try to construct the first row of the matrix. So for instance, to go from vertex 1 to either vertices 2, 3, or 4, you only have to cross one edge. So you put a 1. To go from 1 to itself, you put a 0, because you don't have to do anything. And then to go to the rest of the vertices, like for instance 7, 8, or 9, or whatever, you have to travel to 2 edges. So the distance will be 2. Something more interesting would be like if you go from 2 to 8, you have to travel through 3 edges, so the distance will be 3. So immediately you get that you have a matrix that with zeros on the main diagonal, because to go from a vertex to itself, you do nothing. And that is symmetric, because the distance has been defined in a symmetric way. These two facts are not too surprising. What is surprising was what Graham and Pollak observed. They observed, for instance, that if the tree has 9 vertices, like the one that is drawn, the determinant will be 1024. It will be 1024 regardless of the structure of the tree. The only thing that seems to matter is the number of vertices. And this is a very surprising result. So what happened in general? So you have your tree, you construct the distance matrix, and what the Graham and Pollak showed was that the value of the determinant will be always -1 to the n minus 1 times n minus 1 times 2 to the n minus 2. So they prove it using linear algebra, but the result is very combinatorial. So you see, what does number mean? So the n minus 1, for instance, a first guess will be pick one of the edges, because a tree with n vertices, or we have n minus 1 edges. So you pick one. So what do you do with the 2 to the n minus 2? Well, 2 to the something seems like you are taking orientations of the remaining edges. And then the -1 to the -1, well, this is a bit less clear, but since in a determinant, you are always counting with a sign that comes from the sign of the permutations, from sign of permutation, this should be a sign of something. So we are in 2024. There have been a lot of years from the time that Graham and Pollak discovered their formula. And even if there are plenty of proof, they all seem to rely on linear algebra. You can there are many techniques to compute the determinant. You can do Gaussian elimination. Well, there are many things you can do, but none of them really get to the point like, what does this number really mean? And what's the connection with the determinant? And that was the object of our work and what I wanted to show. So if I develop the determinant, I obtain this sum. This will be a sum of all permutation, the sign of the permutation, and then I will have a product of the distances between a vertex and the image of the vertex under the permutation. This is just the expression of the determinant, except that I'm using the LD because it's the distance matrix. So how can I think about this? I can think that I pick a permutation, either one of those that appear on the signed sum. So I have one at random. So for instance, I send here 1 to 6. Well, how can I think? I can think like I'm going from vertex 1 to vertex 6. And then there are distance too. How I think about that? I interpret it like saying that I'm picking an edge from 1 to 6. For in the example would be the edge 1, 2. So if I look at the picture on the right, I put an arrow in the edge I pick. And since I'm going always from I to sigma I, it's not just an edge, it's an oriented edge. It comes from an orientation. Let's try it with another one. Like in my permutation, 6 goes to 2. No, these are too close. 8 goes to 4. These two examples are fine, but there's only one thing to pick. 1 goes to 6, 2 goes to 5, 1 to pick. 3 goes to 8. Okay, this is interesting. So I have 3 edges, and I pick one. In this example, I pick the edge that goes from 3 to 1, and I mark it with an arrow. And I go vertex by vertex, and then I put the long line, it's a broken line, saying that I go from one edge to another to hit its measure under the permutation, and then the tip of the arrow will tell me which vertex which end of the edges I selected, and in which orientation. And I get something that I would call a catalyst. And catalysts come naturally with a sign. It's just the sign of the permutation sigma. So what the determinant is doing, I can summarize it like this. The determinant is doing a signed sum of all possible arrow flows I can define, of all possible catalysts I can define on a tree. I have a few more examples. And some of them come with positive sign, some of them come with negative sign, and this is decided by the underlying permutation. So I now have a combinatorial interpretation for the determinant. Well, it's not too surprising, I will say, but at least I have something to start with. So what will be our goal? Our goal would be to define a sign reversing involution on the set of catalysts. And ideally, I want that the fixed point all have the same sign. So you have to count the number of fixed points and attach the sign that is correct for my case, and derive the Graham Pollak formula. And this is the idea of what I'm going to present. But the thing is, well, this isn't, we're in the 2024. There are many years. So what's new? Why someone didn't try it before? My guess, and of course this is just a personal guess, is that at this point the natural thing to do will be to group permutation according to to group catalyst according to the underlying permutation. Except, well, this is natural, but the problem is that it doesn't work. So I have the summand you get when you compute the determinant of a path of 4 vertices, just a path with 4 vertices. And I'm grouping the catalyst according to the permutation. And as you can see, there are no cancellations. So this is not helpful. I would like to have something like a plus something, and then the same number with a negative sign, and then define the involution between the classes and know that they cancel. But here there is nothing interesting. Of course, the formula works. If you make the calculation, you get what you should get, but we will have to start by finding a better way to group the catalyst into classes. So we'll define an arrow flow, and an arrow flow will just be a multi-set of arcs on the tree. And the thing is that a catalyst each catalyst will induce an arrow flow. This is the one that I'm using as my running example, and I look at the catalyst and I only see the arrows. I forget about everything else. So on the horizontal part of the tree, I have 2 arrows in opposite directions, and then everywhere else I have an arrow. I want to show 2 more examples to show how what kind of thing I can get as an arrow flow of a catalyst. So in the other 2 examples, see, there are 2 different situations that we have to consider. For instance, in the first one, there is no arrow on the top between vertices 1 and 2. So I just get a hole. There is nothing there. On the second one, well, this is very close to the original example, except that here the 2 arrows are pointing in the same direction. And that makes it much easier to deal with as it will develop. So instead of adding all catalysts at the same, I will group them according to the arrow flows. And then I will add all catalysts inside each arrow flow. So what I'm doing really is to define a partition. And I say that two catalysts with the same arrow flow belong to the same arrow flow class. And then my idea will be define an involution inside each arrow flow. And it will develop that inside the sinus sum each arrow flow is either 0, so I can forget about them, or -1 to the number of vertices -1. That's perfect. Why is perfect? Let me show you. So first, I'm gonna decide when I get 0 and when I get something that is not 0. And look that in an arrow flow, there will be several things that could happen. It can happen that the repeated arrow that they're pointing in the same direction. It can happen that I have to repeat the arrow, but they're pointing in opposite directions, or that I can have a hole. So I will consider 2 classes, or 2 types. If an arrow flow has either holes or parallel arrows, then the sinus sum of all catalysts in that class is always 0. That's by no means obvious, but I'm going to show you later. On the other hand, if it's connected, but the 2 arrow flows are antiparallel, it's always going to be -1 to the -1. Before going through the proof, let me show the implication of this result. So the first thing I observe is that this -1 to the -1 is either always 1 or always -1, depending on whether n is odd or even. But there are never going to be cancellations. So if my result were to be true, you have to count the number of arrow flows without hole and without parallel edges. And for that, I choose an edge, and I do it in that edge. I put anti-parallel arrows, and all others I orient them in any possible way. And then I have to look at the sign, and the sign will be this -1 to the n-1 that the theorem gives me, and that the way I'm going to show that is always exactly that is I'm going to show that the only surviving catalysts have as an underlying permutation and end cycle. So that will be the right sign. So from my theorem, I get immediately the formula of Graham and Pollak. And it also shows that the arrow flow partition is the right partition for this job. It does exactly what I want to do. So let's look at the proof of the theorem. So I will consider three cases. The two that give me zero. The first situation that gives me zero is when the arrow flow have a hole, when it's disconnected. And by the way, when I talk here of connected or disconnected, what I really mean is after I forget the orientations. I forget the orientation and then I look if it's connected or not. So here I have a hole between 1 and 2. So how can I show that the tiniest sum of all arrow flow in this that have a hole is always zero? So I pick an edge with a hole. In principle, there could be many. Well, I pick either one. For instance, ij. And then what I do is I swap sigma I and sigma j, and I also swap the directed edge I pick. So there are two possibilities. What I do is I compose sigma with transposition ij, and I compose the function f that pick one edge on the path with transposition ij. And I have defined an involution. I draw two pictures because the picture doesn't look exactly the same if the image of I and j are opposite sides, but it's the same construction. So I have defined a sign reversing involution that have no fixed point. So the sign sum of all catalysts in that class have to be zero. Then I go to the next case when I have a connected arrow flow, but I have parallel arrows. In this case, I just swap the image of, I just swap, I mean, when I compose sigma with ij, I'm like swapping the end of the path. And then I also swap in f which arrow I select. This doesn't change the direction of the arrow. Again, it's an involution. And then we have proved like the easy part of our theorem, that if my arrow flow have a hole or parallel arrows, the sum of all catalysts inside that class is always zero. So let's go to the other one. And the other one requires more job. You have to work harder. So I'm gonna first give you a description. I'm gonna call this sort of arrow flow unital. And the name unital comes from the fact that they add to a unit, a plus minus one. And the first gonna do is, given a planar rooted tree, well, I also need a bit more, I'm gonna construct a cyclic network called the root map. Then I'm gonna show that from each catalyst, I'm gonna get a family of paths on the root map. And this is a sign preserved bijection. So counting catalysts will be the same as counting families of n paths. And the good thing here is that I have the famous and beautiful Lindstrom-Gesell-Viennotte lemma that assures me that I only have to worry about non-intersecting families of n paths because the other will cancel each other. And finally, I will prove that there is only one surviving family of non-intersecting paths and how to get it. And this will end the proof. So probably the most complicated thing is to construct the root map. So I'm going to go careful there. So the first thing, I have my arrow flow, and this is the one I'm using as a running example. I am going to construct a trie of them. So the first thing I do is where I have the antiparallel arrows, I will add a root R, and I will go from the root to the two vertices that were connecting them. And now I have a tree. And it's a rooted tree, a rooted directed tree. And then I will define a structure on the tree. I want to make it planar. So it doesn't matter too much how I do it. The only condition I really care is that all ascending tree goes before all descending tree, like in the picture. This always can be done, and probably more than one way, but you fix one. So I call this an LR tree, a left-right tree, because I have a set that I call L, that are those that in the left that share the properties that are ascending, grow from the children to the parent. And then I have another group of vertices that are called right, that are descending, and that means that they go from the parent to the child. And my condition, let me repeat it, is that ascending children always come before descending ones. So I have one of my trees. And then from that, I'm gonna call what is called the Irwin tree of my tree. And the idea here is I draw a little circle around the vertex. Then I add each point, I add a vertex at each of the intersection of the little circle with the other edges. And then I add one edge in the middle between the left set and the right set. So I guess it's easy from the picture to imagine why we call it the Irwin tree. However, well, I like the name. It's they look like ears. But what I really thinking when I think about that is not that. I think more like that, like they are runabout, and they are somehow broken so that I cannot make a full turn. So for me, they are more like runabout that there is some sort of defect that doesn't allow me to go around. And if I look at the vertices, I have a vertex from, if I look at the original tree, I have a vertex from each edge of the original tree, and then I have a vertex from the vertex to the parent and from the vertex to it. That is just, the one that separates the left from the right is just something that reminds me of the vertex. Now I do a very classical condition, a construction that is called the line tree. It's called, in my case, it's restricted. I'll tell you later what it's restricted about. But if I have a graph set, the node of my line tree of set will be just the edges, and the edges of my line tree will be the pairs of adjacent edges, except that I add the condition that P and R have to be different. And again, the idea here is that eventually I want to work on something, and I want it to be a cyclic. So I cannot make a recall. If I go somewhere, I cannot go back. That's the point of the condition. So I can do, even if I can do this from any graph set, if I start with a tree, the result has to be a cycle, because pass on a tree, or we have to have a recoil. The only way of visiting a vertex twice is go and come back. So that cannot happen. So in the case where the tree I start is the one I started with, where I gave a plain rooted left-right structure to my tree, to my arrow flow after I add the root, I constructed the Irwin tree. So I can see that I have three, in the line graph, I have three sort of vertices. Remember, the vertices are the edges of the old graph. So I have some that I call B nodes that come from the extra thing that I put in each of the ears. I have some that I call E nodes that come from the vertices that were connecting. Sorry, there is a question. How I see the question?
I think there is no question.
No, it was me.
Yeah.
I put the hands here. Okay, I understand that. Okay, so I have an E node. Each time I connect, I use one of the vertices that was connecting with another vertex in the original construction. And then I have something that I call the S vectors that allow me to cycle around a vertex. I think of them as sectors. So they allow me to move like in the runabout. So what would be the hemisphere of a left to right tree? I just do first the Irwin connection, and then the line connection. So I could describe the arcs, but I think it's better to do in an example in a talk. So I start in one of the vertices, for instance here 4. I start to cycle around vertex 4 in the original tree in my mind, using the sectors until I get to the edge, one of the edges I want to go. So I cross using the edge, and then I start cycling around another of the vertices, and then I cross with an edge, cycling again, an edge, and then I end at some edge. I just cannot move. I could have stopped at any of the edges. Maybe this example suggests that this is the last one, but no. I can stop at, I start in a vertex, and then I stop at any of the edges. So the idea here is to turn my hemisphere into a network, and I say the sources are the vertices, and the sinks are the e-nodes, what in the original tree representing the edges. So how do I define the root map? So I have my original hemisphere that I will call the southern hemisphere. I do like an anti-isomorphic copy. I don't want to go to all the details, but essentially I take the mirror image as is indicated in the image, and I call the mirror image the northern hemisphere, and both of them are acyclic because I have started with a tree. I constructed the Aryan tree that is also always a tree because I'm just drawing. Essentially, I use drawing in a different way, and then I constructed the line graph, but the restricted line graph of a tree is always a tree. So I have two acyclic networks. And then I put a lot of bridges between them, and essentially I join each edge with its copy each edge in the southern hemisphere with the anti-isomorphic copy in the southern hemisphere. So I can go through one edge to the copy one edge in the south to his copy in the north. And when I put all this information together, I have the root map. Look that it have to be acyclic because there are no cycles in the south, there are no cycles in the north, and the bridges go in one direction. So there is no possibility. And then I give it the structure of a network, saying that the sources are the node in the vertex node in the south, and the sinks are the vertex, but now the image is in the north. So let me show now how to transform a catalyst into a walk in the root map. So suppose I go from, I take the path that is in dark color. So I'm going from 9 to 1 in the catalyst. The idea is here. I always start in the south. I start at vertex 9. I start to cycle until I get to the edge I want to take. In this case, there was no choice. Then I start to cycle until I get to the next edge. And at the moment I get to a bridge, I go to the north. And then from here, I go out, and I end at 1. So what I'm doing is like a translation from a catalyst to a path. So, but a catalyst will have many paths in them. So here I put all the numbers, and let's do one. For instance, from 3 to 1, I start at vertex 3. Essentially, at this vertex 3 is here. Since this is the marked one, I go to the north, and then I start to circle the thing that I can. Okay, then I start to circle until I get to 8 tilde, and the little numbers tell me. So I'm here. I take the north, and then I start circling the north until I get to the 8. So what I have defined is a sign reversion bijection. I wrote bisection, I don't know why. Bijection between the set of catalysts inside an arrow flow and the families of n-paths in the root map that correspond to that arrow flow. So they have the same sign sum. And now we can rely on the lemma of Limstrom-Gesell-Vienot that tell me that if I have any network with a set of sources and a set of sink, and I want to take the silent sum of all families of paths from a sink to from a source to a sink, and I do it in all possible ways, I only have to consider non-intersecting paths because all other cancel each other. So my original problem that was doing the silent sum of all catalysts in an arrow class becomes doing the silent sum of all families of paths in the root map. That's what I denoted RR. I don't think I defined it before, but this is the root map. And now I can describe which one is the only non-surviving family of paths on the root map. And it turned out that it's exactly one. And not just that, it's a very natural one. So you start working on the root and do the deep first search walk on the tree. So you start moving, and when you get to a child, you go up until you get to the parent, and then you go down, and then you visit each child, and then you go up, and then you go. Can you see? If I do that cycle walk, I will visit all the all the vertices of the tree, and at each and I'm also have the information of which bridges I'm using. And this is a cycle because I start and end at the same number, for instance, 1. And also because I don't go back to 1 until I get back, until I do the complete walk. So the sum will be -1 to the n minus 1, always. And this is the only non-intersecting path inside that particular root map. There could be the many others that belong to the class, they do cancel each other. So we obtain the second part of our theorem. This will be -1 to the n minus 1. We have this otherwise is the interesting case, is the unital case. So, and adding 1 for each unital class, or -1 depending on the parity of n. And let's remember in how many times I will get -1 to the n minus 1. Well, I have to choose the position of the antiparallel edges, and I do that in n minus 1 ways because a tree with n vertices have n minus 1 edges. I have to choose the orientation of every other edge, and then the -1 to the n comes from the fact that I'm doing the deep search walk, that is a cycle. And that's the only one that survived. So what sort of application we have obtained of our formula? In the work that I'm sitting here, it's in the archive, it's the title of the talk. We found a way of describing all the formation and even finding some new ones of the Graham Pollak formula. What I mean is like, what happened if I orient the edges and I define an oriented distance? What happened if I put weight on the edges? What happened? There are many known formulas, and they are all very similar and very, but again, there was no proof for the original formula. And for this one, there was a collection of techniques from linear algebra. They were not very coherent. So we can do now all of them very uniformly. And also, and the reason is that we verify that the different weights we put on the edges or on the oriented edges are invariant by the family of involution we have defined. So we essentially get them by free. Another nice application, it was done by 2 of the authors, not me, by Álvaro Gutiérrez and Adrián Lilo. And they look at it. If you have the distance matrix of a tree, what happened with the minors, with the principal minors? What can you say about them? Well, there were existing results on the literature, and they found that our combinatorial approach, well, it have to be improved a bit, but essentially work for dealing with all of them. And they even found nicer formulas in some cases. And this is what I wanted to tell you. This is a picture of almost all of us. This is Adrián Lilo, Luis Esquivia, myself, Ira Gesell. We dedicate the work to him, and Álvaro. So thank you for listening.
Okay, thank you so much. Thank you so much for your wonderful talk. Let's see if there is any question from the audience. Any question?
Hello, Rosa.
Hello. Nice to see you.
It's a very nice talk and short as well. But it's a really nice talk. Okay, I have one question. Is there any work for different kind of graph? This is just for the tree graph. And do we have this kind of work for other graph which are non-tree?